In this video lecture, we're going to learn about the Offeror Principle and we're going to learn how to write the electronic configuration. But before moving on and writing down the electronic configuration, I would first revise what we have studied in the previous video lectures. The first thing that we discussed were orbitals, and orbitals were regions where there were high probabilities of finding an electron around the nucleus. So we did all sorts of orbitals. There was an s orbital, a p orbital, a d orbital, and an f orbital. An s orbital had a spherical shape, so the region where there was a higher probability of finding an electron was a spherical region around the nucleus where there was a very high probability of finding an electron. A p orbital was dumbbell shaped. It had two lobes. There were two regions around the nucleus where there was a very high probability of finding an electron. A d orbital was flower shaped or clover leaf shaped. It had four lobes, and there were four regions where there was a very high probability of finding an electron if an electron was in the d orbital. And then you had an f orbital, which had most of the f orbitals had 8 lobes. So this is the first thing that we discussed, the types of orbitals. And we also discussed that each orbital has a maximum capacity for 2 electrons. And the 2 electrons must have opposite spins, which means that they must have opposite magnetic fields, magnetic dipoles, so that the electric field of repulsion gets cancelled out by the magnetic force of attraction, so that 2 electrons do not repel each other. So they must have opposite spins or opposite magnetic dipoles. The next thing that we discussed was subshells. Now, subshells were basically a bunch of orbitals grouped together. So you had an s subshell. An s subshell consisted of only one s orbital. So it only had one s orbital. So an s subshell can accommodate a maximum of 2 electrons because it only had one orbital. Then you had a p subshell. When you talked about the p subshell, you were basically talking about the px, py, and pz orbitals together. So there were 3 orbitals in a p subshell, and since each orbital accommodates a maximum of 2 electrons, so 2 electrons each in each of the 3 orbitals would give you 6 electrons. So the p subshell can accommodate a maximum of 6 electrons. Then you had a d subshell. A d subshell had 5 d orbitals, and since it had 5 d orbitals, each orbital accommodating 2 electrons, that would mean that a maximum of 10 electrons can be accommodated in the d subshell. Lastly, you had the f subshell, which had 7 f orbitals. So 2 electrons in each of the orbitals would give you a maximum of 14 electrons. So the f subshell could accommodate a maximum of 14 electrons. Then we also discussed Hund's rule, which is that when you're filling a subshell, so a subshell has a number of orbitals. So if you're filling a subshell, so electrons would occupy the subshell, the orbitals in the subshell, in a single manner first. So for example, if you're filling the p subshell, one electron would first go into the px orbital, then one would go into the py orbital, then one would go into the pz orbital. Once each of the orbital has one electron each, then a second electron would go into the px, then a second electron would go into the py, and then the second electron would go into the pz. So orbitals in a subshell would always be filled in a single manner first. The reason is because they are completely identical orbitals. They have the same energy level. For example, p subshell, the orbitals, the only difference is in the orientation of the orbitals. So one electron goes each in the orbitals, because if one electron goes into the px orbital, the other orbitals are empty. So the other electron would prefer an empty orbital because there would be less repulsion. So remember this: electrons always fill subshells in a single manner first. The last thing that we discussed was about shells. And remember, shells were energy levels. They were also called principal quantum numbers. So a given shell of an orbital would describe the energy of the orbital or subshell. So if an orbital or a subshell had low energy, that means that the region would be close to the nucleus, the electron would be less energetic, and it won't be able to go very far away from the nucleus. If or vice versa, if a shell had high energy, so that means that the electron would be further away from the nucleus and the electron would be more energetic. It could occupy regions much further away from the nucleus. So I've drawn 3 orbitals, s orbitals. So there's a 1s orbital, which means that it's in shell 1. The s orbital is in shell 1. So the region that the electron is occupying is very close to the nucleus. It's not very energetic. If an orbital is in shell 2, so this over here is the 2s orbital, which means that the electron in the s orbital is more energetic. It's in the second shell. So the electron is more energetic. It occupies regions much further away from the nucleus. It's more energetic, so it could overcome the strong force of attraction from the nucleus and go much further away. Similarly, if the orbital is in 3s, that means that the electron is even more energetic, so a spherical orbital would be much bigger in size, and the electron would possibly occupy more regions much further away from the nucleus. So as the shells increase, the energy levels are going to increase. A lower numbered shell would have low energy. A higher numbered shell electron would have much higher energy. Now I'm finally going to discuss the Offeror principle. And this principle states that low energy subshells would be filled first, and low energy subshells are the ones that are closer to the nucleus. So we're going to start off by filling shell 1. That's the lowest energy orbital subshells. They would be very close to the nucleus. Then I'm going to fill the subshells in shell 2, and as we move, we fill shells which are further away from the nucleus. Electron will be more energetic. It's going to occupy regions much further away from the nucleus. So you have plenty of orbitals. What you're going to do is you're going to draw this table. It's very easy to actually draw this table. You start off with 1s, 2s, 3s, 4s, etc. and so on, and you keep on writing. Now there's a 1p missing over here. There's a 1d and a 2d missing over here. So you have written all these orbitals till f orbitals. So there's a column representing s orbitals. This 1 stands for the shell number. So the first shell only has a single s orbital because it's very close to the nucleus. There is not a lot of space around the nucleus when you're very close to the nucleus. But as you move further away from the nucleus, the electron becomes more energetic. So if you're talking about shell 2, it's going to have 2 subshells. One is the S subshell and the other one is a P subshell in the second shell. Then as we move further away from the nucleus, in the third shell you have even more subshells. So there's going to be a 3s subshell, a 3p subshell, and a 3d subshell. And so as you move further and further away from the nucleus, the electron becomes more energetic. So in the fourth shell there's going to be an s orbital, a p orbital, a d orbital, and an f orbital. So if you count the number of electrons in the first shell can have a maximum of 2 electrons because there's only one subshell and that subshell has only one orbital. If you look at the second shell has 2 subshells. An s subshell that could accommodate 2 electrons and a p subshell that can accommodate a total of 6 electrons. So that's a total of 8 electrons in the second shell. If you look at the third shell, you have an s subshell, a p subshell, and a d subshell. There are 5 orbitals over here, 3 over here, and 1 over here. So that's a total of 18 electrons. And so as you move to the fourth shell has 4 orbitals, an s, a p, a d, and f. F has 7 orbitals, d has 5 orbitals, p subshell has 3 orbitals, and s subshell has 1 orbital. So that's a total orbitals of, you can count them, 7 plus 5 is 13, 13 plus 3 is 16. So that's 7 plus 5 is 12, I think, and 12 plus 3 would be 15, 15 plus 1 is 16. So you have 16 orbitals, and that would be a total of 32 electrons in the fourth shell. Now the way you're going to fill the orbitals is you're going to follow the arrows. So if you're going to fill electrons in subshells, the rule is that you're supposed to follow the arrows. The arrows would indicate and follow the arrows downwards. So the arrows are going to indicate which subshell would be filled first. So if you look at this, the first arrow is this one. So if I follow this arrow, there's a 1s subshell. That 1s subshell would be filled first. That would be the one that would be closest to the nucleus, and electrons are going to occupy that particular subshell first. Then start following the second arrow. That has a 2s subshell. Then once 1s subshell is filled, you're going to fill the 2s subshell. After 2s subshell, follow the third arrow. The third arrow, you have a 2p subshell followed by a 3s subshell. So the order is going to be, you're going to fill a 2p subshell, and after that you're going to fill a 3s subshell. Then I'm going to follow the fourth arrow. The fourth arrow indicates that the 3p subshell would be filled, and then 4s subshell would be filled. So after that, a 3p subshell would be filled, and after 3p, a 4s subshell is going to be filled. And if you keep following the arrows, following the fifth arrow downwards, it's going to be 3D followed by 4P, then 5S. So it's going to be 3D, 4P, and then 5S. So as you keep following this, these arrows downwards, that would give you the order in which the subshells are going to be filled. So you're going to start off with the lowest energy subshell in the first shell. So that's your lowest energy subshell, and you're going to start filling orbitals in and subshells in this particular order. So either you can remember this order, so that's one thing that you can do. You can remember the order in which the subshells are filled, or what you can do is you can learn how to construct this table. It's very simple. Write down 1s, 2s, 3s, then 2p, 3p, 4p, etc., then 3d, 4d, 5d, etc., and then draw diagonal arrows which are going to intersect the table, and that would give you the order in which the subshells are going to be filled. So now I'm going to try and fill electrons in these subshells, starting with very small atoms. So let's pick the example of lithium. Lithium has a total of 3 electrons. Now if it has 3 electrons, the first electron would go into the 1s subshell, and the 1s subshell has only one orbital, so that's 1s, and you're going to write 2 on top. This 2 would indicate the number of electrons that could be accommodated in that particular subshell. Now once 2 electrons are there, you're only left with 1 electron, so that 1 electron would go into the 2s subshell, so that 1 electron goes into the 2s subshell. Now to understand what a lithium atom would look like, there are 2 electrons in the 1s subshell. So the 1s is going to be a spherical orbital around the nucleus, so that there's going to be a very high probability of finding an electron around the nucleus in a spherical region around the nucleus. So this green shaded area is going to be your 1s orbital. And then, so this is your green shaded area, that's your 1s orbital. Then there's going to be a very high probability of finding an electron in a 2s subshell, that is basically 2s orbital. It has 1 electron. So there's going to be 1 electron in this particular region, spherical region around the nucleus. So there would be 2 electrons in this spherical region, and there's going to be 1 electron in this larger spherical region. So this is what the lithium atom would look like. Now I'm going to try and write the electronic configuration for boron. So the electronic configuration of boron is going to be, and I'm going to follow the same orbitals that I got from this table over here. So if I write the electronic configuration of boron, 1s subshell would be filled first, so 2 electrons go in there. 2s subshell would be filled after that, so 2 electrons would go there, so that's a total of 4 electrons. Now after 1s and 2s, you have the 2p subshell that would be filled first. So remember, this 2p subshell, there's only 1 electron left, so 1 electron would go into this 2p subshell. And if you're thinking about the 2p subshell, remember the 2p subshell is made up of, and if I try to explain this 2p subshell is made up of 3 p orbitals. One is the 2px, the other one is the 2py, and the third one is the 2pz orbital. So it's made up of 3 orbitals. So since it has 1 electron, so 1 electron goes into the 2px, the other 2 orbitals in the subshell are going to be completely empty. So that's the electronic configuration of boron. Now I'm going to try and draw the atom of boron. So this is what a boron atom would look like. So I'm going to explain this. 2 electrons in the 1s orbital, 1s subshell. So that means there are 2 electrons in a 1s orbital. So I'm going to shade that. Very close to the nucleus is going to be a spherical region, and there would be 2 electrons in this spherical region very close to the nucleus. So there are 2 electrons in this spherical region close to the nucleus. Then you have 2 electrons in the 2s subshell, which means that there is a 2s orbital which is slightly more energetic. So it's a spherical region around the nucleus. There's going to be a very high probability of finding an electron, but the spherical region would be much further away from the nucleus. So there are 2 electrons in this spherical region over here. So there are 2 electrons in this green region that I've shaded. There's a high probability of finding 2 electrons over there. And then you have 1 electron in a 2p subshell, which means that the 2px orbital has 1 electron. So I've 2px orbital has 2 lobes. So I've drawn these 2 lobes. So there's going to be a very high probability of finding electrons and just 1 electron in this dumbbell shaped region around the nucleus. And remember that an atom, the nucleus is in the center, it's attracting all these electrons. 2 electrons in this tiny spherical region over here, that's your 1s. 2 electrons in this larger spherical region, it's more energetic, so that's your 2s subshell. And 1 electron in the 2p subshell, so just one of the 2p orbitals would be filled and it would only contain 1 electron. So this is the shape of a boron atom. And remember one thing, that the orbitals, the electrons in the orbitals, the regions are overlapping. This spherical region and this larger spherical region, they overlap and they exist in the same area, but 2 electrons, the electrons in these orbitals, they would not collide with each other. The reason is that both electrons are basically negative. So if 1 electron is over here, the other electron cannot be in that exact same spot because the 2 electrons are going to repel each other. So there are no collisions happening between the electrons, except for the fact that the orbitals and the regions that they are occupying are overlapping. In this third example, I'm going to write the electronic configuration of fluorine. I've written the electronic configuration of fluorine. So again, I'm going to follow the same low to high energy orbital arrangement that we discussed earlier. So 2 electrons would go into the 1s orbital subshell, 2 electrons would go into the 2s subshell, and 5 electrons would go into the 2p subshell, which means that 5 electrons going into the 2p subshell. So if I expand this 2p subshell, it has 3 p orbitals. One is the 2px, the other one would be the 2py, and the third one would be the 2pz. So if I have 5 electrons, so 2 electrons in 2 orbitals and 1 in the last one, so that's a total of 5 electrons in the 2p subshell. Now I've drawn the atom of fluorine. So there's an s orbital having 2 electrons, but it's in the first shell, which means it's going to be very close to the nucleus. So if this here is the center, is the nucleus, so there's going to be an electron roaming around in a spherical region around the nucleus, very close to the nucleus. So there's going to be a very small spherical region, an s orbital of the first shell. Then after that, there are 2 electrons in the 2s subshell. So there's going to be an s orbital, much bigger in size because the electron is going to be more energetic. So this region would be much bigger compared to the. So there would be 2 electrons in this spherical region around the nucleus. So there are 2 electrons in this spherical region, and then I have the 2p subshell. Now the 2p subshell has 2 electrons in the 2px, 2 in the 2py, and 1 in the 2pz. So I'm going to shade 2 electrons now. So there would be 2 electrons in, let's call this the 2px orbital. So there would be 2 electrons in this 2px orbital, and there would be a further 2 electrons in the 2py orbital. So 2 electrons in this particular orbital, and there would be only 1 electron in the 2pz orbital. So this is how a fluorine atom would look like. A spherical region around the nucleus, very close to the nucleus, having 2 electrons. Another spherical region, but this time much bigger in size, that would accommodate 2 electrons in this particular region. And then there would be 2px, 2py, and 2pz orbitals. So 2 electrons in the 2py, 2 in the 2px, and 1 in the 2pz orbital. I am now going to try and write the electronic configuration of a bigger atom. And the example is for iron. It has 26 electrons. So again, I'm going to use the table that we constructed in the Offeror Principle. So starting with the lowest energy subshell, 2 electrons would go into the, so I have to fill 26 electrons. 2 electrons would go into the 1s orbital, so there would be 2 electrons there, followed by 2s, then there would be 2p, then 3s, then 3p, 4s, etc. So I'm going to follow the arrows down. So 2 electrons in the 1s orbital, 1s subshell, 2 electrons in the 2s subshell, Then after that, I would have 6 electrons in the 2p subshell. Remember, there are 3 orbitals in the 2p subshell, so each accommodating 2 electrons would make 6 electrons. After 2p, I have the 3s, then 3p, then 4s. So there would be 2 electrons in the 3s subshell, followed by 6 electrons in the 3p subshell. After which there would be 2 electrons in the 4s subshell, and after 4s I would be left with the 3d subshell. So following the arrows, I have reached 3d subshell. Now I need to count the electrons, so that's 2 plus 2, that's 4, plus 6 is 10, 10 plus 2 is 12, 12 plus 6 is 18, 18 plus 2 is 20. So I'm left with 6 electrons, so 6 electrons would occupy the 3d subshell. So in this way, this is how 26 electrons of iron would be filling all the subshells. The next atom I'm going to write the electronic configuration is an even bigger atom, and that's iodine. It has a total of 53 electrons. So again, following the arrows down this table, I would fill all the electrons according. So it's starting with 1s. So I now have to fill 53 electrons. So starting with the 1s subshell, 2 electrons in that. Then the second 2s would 2 electrons in the 2s subshell, then 6 electrons in the 2p subshell, after which there would be 2 electrons in the 3s subshell, after which there would be 6 electrons in the 3p subshell and 2 electrons in the 4s subshell. So I've reached this point over here. So 1s, 2s, 2p, 3s, 3p, 4s. Now it's 3d and then 4p. So 10 electrons in the 3d, and then followed by, I would have the 4p subshell. Now one thing that I need to be careful about is I need to count the total number of electrons. So it's 2 plus 2 is 4, plus 6 is 10, 12, then 18, 20, then that's 30. So 6 electrons in the 4p subshell, so that would be 36. So I've reached 36. So after 4p, 5s subshell would be filled. So that's 38 electrons, and after 5s, 10 electrons would go into the 4d subshell. So that would make it 48, and now I'm left with 5 electrons. So it's going to be 5. P would have 5 electrons. So that's a total of 53 electrons of iodine, and this is the electronic configuration for iodine.